has captured the imagination of lots of people. This is becoming a big thing. I seem to be having an international reputation now about exploding dots. I get asked all over the place to do exploding dots. There's something about it that's appealing. It really does connect K through 12 and university level work and unsolved research problems mathematicians are still working on this day. It's got the whole shebang. And it's absurdly simple. It goes as follows. I begin with a story that's not true. And when I was a child, in this untrue story, I invented a machine. Not true. And all the machine is a row of boxes. Does it go as far to the left as ever I desire. And being somewhat precocious child, it gave this machine a name. It gave it a very strange name. I called it a 2-1 machine. And what you do in this machine, you put in dots. So I put in 1 dot. Dots always go in the rightmost box. Zoom. And nothing much happens, it says 1 dot. Not very exciting. Put in a second dot, however. Always the rightmost box. Zoom. Whenever there are 2 dots in a box, they explode. Kapow! They become 1 dot, 1 place to the left. Hence the name 2-1 machine. Yeah? Okay. So for the code for 2 in this machine is no dot, no dot, no dot, no dot, no dot, no dot, 1 dot, 0 dots. I'm not going to bother writing the leading zeros, I'll just write the code is 1, 0. Here comes the third dot. Always the rightmost box. Zoom. So the code for 3 is 1 dot, 1 dot. Sorry? Is it? Cool. Let's keep going. Maybe it is. Remember, I'm a young child. I don't know anything. Put in a 4th dot. Can you see what's going to happen? It's very exciting. Here comes 4th dot. Zoom. Kapow! Then what happens? Kaboom! So what's the code for 4? 1, 0, 0. Put in a 5th dot. What'd you get?
1, 0, 1.
Put in a 6th dot. What'd you get?
1, 1, 0.
Sure. Put in 13 dots. What'd you get?
1, 1, 1.
Oh, tricky. Seriously, put in 13 dots. What do you get? Type something another website in here.
Yeah, you
For later on.
should be good.
About 6 hours.
It might be ready for my page.
1101.
1101.
Second.
Colin, what'd you get?
It's actually one of the ungraded.
So put 13 on board.
I took class 3, I don't count as high as 13.
So I heard 1101. Any other answers? 110. Heard that again?
Palmer, can you please come to the office?
Okay, I've heard it 3 times. It must be true. I hear something 3 times. It must be right. We'll go with 1101. Anyhow, hours and hours of fun to be played with a 2-1 machine. But then, in my untrue story, one day I had an epiphany. Instead of a 2-1 machine, I realized I could do a 3-1 machine instead. How's this one work? Wheels explode, become 1 dot, 1 place less. So put in 1 dot, what happens?
Nothing.
Next. Put in a second dot, what happens?
Nothing.
Null. Put in a 3rd dot, however. 3 dots explode, kaboom! 1 dot, 1 place to the left. So the code for 3 is 1, 0. The code for 4 is code for 5. Code for 6. 2, 0. Code for 13. Oh. Done it again. Annoying with me. Skip some numbers. What's the code for 13? 111? Yeah? Have I heard it 3 times yet? Have you heard it 3 times yet?
Yeah.
I
That's what I
have.
got.
111 apparently. Hours of fun we have with a 3-1 machine working out codes of lots of different numbers. Then, another epiphany. So with a 3-1 machine, I could do a 4-1 or a 8-1. Anything. But let's go all the way up to a 10-1 machine. And let's be wild. Let's put in 273 dots in the 10-1 machine. What's the secret code for 273 in a 10-1 machine?
273.
I know many of you are completely on to me. But is it obviously 273 in my story so far? Yeah? I'll do it. I'll put in 273 dots. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. Tell you when it's boring.
Next.
Not yet.
Right, not yet. Can I just write the number 273 for the actual 273 dots? Alright. So let's be really slow. I'm much slower than you guys. Will there be some explosions? Just a yes/no question.
Yes.
There'll be explosions. How many explosions will there be right off the bat? 27 explosions. There's 27 groups of 10 in there. Will there be any dots left behind? There'll be 3 dots left behind. So 3 dots left behind, 27 explosions. Each explosion makes a dot. How many dots will appear there? 27. Alright. What will happen next? There'll be 2 explosions. Any dots left behind? 7 dots left behind. That's a smudge. 2 explosions, each make a dot, so there must be 2 dots here. So what's the code for 273 in a 10-1 machine? 273. You're completely on to me. What are these machines really doing? What's going on? Alright, now, you're speaking very adult language to me. Yes, absolutely right. We're doing binary, we're doing ternary, we're doing base 10. But can you really get at the heart of what's going on? As a teacher now, I don't know what base means. How do you explain what's happening in these machines really? Sorry? I guess we're talking about place study. You all give me all the adult words, which is great. Yeah? So let me help you out. It is true, I set up these machines, I'll go to the very first one again. If you put in 1 dot here, I've always made that worth 1. And then we said, when you get 2 dots here, that's equivalent to 1 dot there. So that dot better be worth 2 ones. It better be worth what then? 2. 2 of these guys, we said, is worth 1 of those. So that better be worth 2 2s. 4. 2 of these makes 1 of those. This better be worth 8, 16, and so on. Beautiful. 3 people said that 13 is 1 1 0 1. You said 1 dot, 1 dot, no dots, 1 dot. Can you now see that really is truly the correct answer? Yep, it says 1 8 and 1 4, no 2s and 1 1 really does make 13. Yes, and we call that base 2. We call that binary. So in base 3, what's going on here? What's really happening in the machine? Back to very basic principles, I say these dots are always worth 1, so I've set the game up, always put 1 dot there, 1 dot there, 1 dot there. But then what happens? 3 of these are worth 1 of those, it's going to be worth 3 of these makes 1 of these. 9.
Good morning, St. Joe's. It's Wednesday today, and on Wednesdays we wear pink, of course, to support and thank you to all those who are wearing pink
Check.
t-shirts today.
You said 1 dot, 1 dot, 1 dot. Are you correct?
Grade 10 and 11
See, you're
students.
correct.
You're
And this guy,
invited to an information session
we
on
work with
social
1,
programs.
10 of these is 1 of those,
They're the
10 of
oil
these is
and
1 of
gas
these, we work
operator
with
and the water waste
10 times
waste
100,
operator.
1,000,
November 24th
10,000,
at 10:15.
so on.
Sign up in Ms. Cutler's office with
I have to talk about that.
The last day for discovery registration is Thursday, November 19th at the school, and Friday, November 20th at the church. Please get your forms in before these dates.
Attention all grade 9s. Remember to hand in your discovery forms to either the office or at St. Joe's Church before November 20th. It is a weekend you don't want to miss.
Any grade 9 please meet in this
These
lobby
announcements tend to go for a long time.
Tuesday, April 20th.
Okay.
All students who sign up for honor roll pizza lunch. Today we will be doing things a little different. Please line up across from the library by the staff room door, and you will enter through there to get your pizza. You must have signed up previously in order to get a pizza. Attention all grade 12 students. We would like to see you registered on my class by the end of the first semester. If you have not registered in my class, please see Principal Valerie in the office. She will help you sign up.
And finally, we have today's specials at the canteen. Hawaiian pizza is $3, vegetable soup $4.50, poutine small for $4, and a large for $5.50. Have a great day, St. Joe's. That's all for me.
Great. All right, so we've just discovered place value, we've just discovered base values, we've discovered all that great stuff. We're in like grade 1 or grade 2 right now. Here it is, all before us. 10-1 machine. We tend to speak 10-1 machine, and I say that literally. We speak 10-1. When I write out the number 273, we literally say 200. We say 200. There they are. 7T. Do you know what TY is short for? Well, obviously, really short for 10 and 3. We literally say 200, 7 tens, and 3. We speak 10-1. Computers speak binary. Why is this base 2 system best for computer work?
On and off.
Because all base electrical switches are going to be on or off. The best way to code on is maybe with a 1, off with a 0. You've got 2 symbols naturally in electric circuits. It seems very natural to code all of mathematics with just 2 symbols, 1s and 0s in binary. There is talk of creating optic computers based on polarized light. You have light that's polarized in one direction, or light that's polarized in the orthogonal direction, or have no light. In which case, they've got 3 possible states. So if optic computers ever really happen, they'll be naturally base 3, using 3 different symbols. We, in society, seem to have globbed on to base 10. Why do we humans like base 10? Because we're confronted with 10 all the time. It's in our anatomy. We're trained to think. Our brains are trained to think 10. Martians have 6 fingers in each hand. So what machine do they use? Base 12, or maybe do one hand base 6, who knows? Some societies are actually base 20 on this earth. Where's that coming from? Fingers and toes. I know I'm not in the US right now, but how does the Gettysburg Address begin? 407 years ago. How many years ago is that actually? 87. The score is 20 years. There's a little bit of base 20 in that language right there. 407. In fact, how do you say 87 in French? Okay, I don't speak French, but set. Translate that literally word for word.
4 20s and 7.
4 20s and 7. That's a vestige of base 20 right there. All right. So I'm going to stick for now in base 10. We'll do 10-1 machines. Because I've got to stick about grade 1 or grade 2. Let's get into about grades 5, 6, 7 right now, and start doing arithmetic. I'm going to take us through the entire grade system. I'll even get us the research stuff. All right. So you've got numbers. You can write numbers. What do you first do with numbers? Addition, add them, okay. You tend to add numbers, one of the first things you do. So let's do like 276 plus 124. Oh, it's too hard. 121. My brain says 2 plus 1 is 3, 7 plus 2 is 9, 6 plus 1 is 7. Just go from left to right. Am I correct?
Yes.
Yeah? I was taught to read left to right. Let me go left to right. Does that perturb you at all? Maybe I chose 2 nice examples. Are you hearing? So what if I chose 145? Is that more juicy? Okay, but I read left to right. 2 plus 1 is 3, 7 plus 4 is 11, 6 plus 5 is 11. The answer is 311. You got me. Am I philosophically and absolutely and even mathematically correct?
Yes.
I am. What I've done here is 10-1 machine, 200s, 700s, and 7 tens and 6 ones, and I'm saying, please add 1 more 100. Sure. Please add 4 more tens. You bet. Please add 5 more ones. Okay. Do I really have 3 hundreds? Do I really have 11 tens? Do I really have 11 ones? I'm absolutely correct. Mathematically, a totally fine answer. No problem. Trouble is, the rest of all thinks I'm strange. I'm saying 311 to 11. How can I fix up that answer for the rest of the world?
Move the values over one when you have a double digit.
Sure. In my language, what would that be? I agree with you.
You explode.
Yeah. So let's take 10 dots from here. Take 10 explode, 4, 4, and 2. That leaves 1 dot left over. Kaboom! Extra dot there. The answer is now 410 to 11. Or 1 to 11. Do it again! 10 explode, kapow! 1 dot left behind, extra dot here, 421. Is that right? Great. So what's the traditional algorithm say to do? Because most teachers in the lower levels get really a little bit stroppy with me. What does the traditional algorithm do right now? Which is weird. Notice you're being taught to read right to left in math class. Everything else is left to right in the world except for math. You go 6 plus 5 is 11, but you're not allowed to write 11, are you? And they call it carry 1. What's really going on right there? What did I just actually do in terms of dots and boxes? I took 10, exploded away, left 1 behind, and this carry 1 is really add an extra dot to the tens place. Right, now I've got 1%, so I get 12 or something, don't I? So you don't write 12, you do an explosion, 4. So the standard algorithm has you explode as you go along. I'm weird, I just do it, and then worry about explosions at the end. It's just a style thing, that's all it is. Alright, long addition, perfect. Let's whip on through. After addition, what do you do next?
When you're doing your math, do you actually work?
Me personally?
Yes.
In the days when I was balancing my checkbook by hand, which is sort of now long over, yes, I was add up the ones, add up the tens, actually I add up the thousands, really. Thousands, hundreds, tens, ones,
Yeah.
get some number at the bottom and just quickly fix it up. It's so much easier. For me, whatever floats your boat, go for it.
Did you ever have anybody else that worked that way with you, or you just came up with that idea on your own?
I guess I'm just weird, I came up with my own. Yeah. Because it just seems natural to me.
How-
It's very hard for us adults to step back from what we're being trained to do.
Do you remember how old you were when you came up with it?
Young adult life.
Okay, so
Yeah.
like university.
Yeah, investigation. When I was actually starting to balance the checkbook, actually.
Yeah.
Yeah. Alright, after addition, what do you do next? Subtraction. It's actually too hard. Let's do multiplication, it's easier. I'd like to know what 2,786 times 3 is. I want the quick, obvious, 2-second James Tanton answer. Just write me the correct answer, write down. No thinking. Just write down the answer. Don't do any work. I'm a mathematician, I hate work. I'll work hard to avoid hard work. What is the obvious, quick James Tanton answer? 6, 21, 24, 18. Philosophically, is this right? If I give you 2,000s, 700s, 8 10s, and 6 1s, and I say, triple everything. So 2,000s, would you indeed have 6,000s? So 700s, would you now have 2100s? 24 10s now? And 18 1s? You're absolutely right. That is an absolutely correct, fine answer. Mathematically valid, no worries with that. Could we fix this up for the rest of the world? Do you want to fix up for the rest of the world right now? Go for it. Fix up for the rest of the world right now.
8,358.
Pretty swift. And you might think this way, you can start doing it pretty quickly. 7,000,
8,000.
8,358.
Yes.
Did you do explosions in the systematic way, or did you just do them randomly? I'll do it randomly just for fun. I explode 20 from right here. 4 behind, extra 2. Now we'll do this one next. 10 explode, leaving 8 behind, make that 5. Beautiful. 8, 3, 5, 8. By the way, actually, I did have an experience in the US when I first came here. I had to write a check for $1,200. Must be some tuition thing as a graduate student. And I was told by the bank teller I wasn't allowed to write 1,200. I had to write 1,200. Because I have a feeling this bank teller told me, you can't have 1,200s. 1,200s explode, things explode obviously, 1,200. Isn't that weird? We do speak this funny way on occasion. We allow ourselves to say 2,100 instead of 2,100. We don't allow ourselves to say 1710s or something, or 1710. Sadly, because it's kind of quirky fun. All right, addition, multiplication. Let's do subtraction now. Let's do 568, take away 312 or something. All right, my trouble is I don't believe there's any such thing called subtraction. I don't believe in subtraction. To me, subtraction is really addition. Well, what am I adding?
Negative.
Negative, yep. I'm adding some kind of opposite. I've got dots, and now I'm adding a negative version of dots, the opposite of dot. All right, so that means if I've got a dot, I'm going to need the opposite of a dot. What should I draw for the opposite of a dot? Okay, so like a hollow dot. I'll call it an anti-dot. It's like matter and antimatter. Because what happens if you put a dot and an anti-dot next to each other? They annihilate. I won't go explode because I've got explosions going on somewhere else. These go. Have you spelled? And you end up with this picture, which is nothing. That's an actual picture, by the way. Right there. Period. Alright, so put a dot and an anti-dot next to each other, and they just annihilate. So what's really going on in this example, in my 10-1 machine, I've got 500s, 6 10s, and 8 1s. And I say, please add the anti-version, that is, add 3 anti-hundreds, there they are, add 1 anti-10, and 2 anti-1s. So far, so good? Will there be some annihilations? Lots of them. I'm left with 2, 5, 6. It's as though I just went left to right again and said 5 take away 3 is 2, 6 take away 1 is 5, 8 take away 2 is 6. And after all, these annihilations do the same thing as subtraction, one thing subtraction. Great, left to right again. Everything is left to right in math. Except in school. So are you worried about my example being too friendly? Okay, let's make it 512, take away 368. Let's switch the final 2 digits. That's juicier. Alright, here's the answer. Left to right. 5 take away 3 is 2, 1 take away 6 is negative 5, 2 take away 6 is negative 6. That's 250 negative 60. Just left to right and just do it. Am I right? Philosophically? I might be weird, but am I right? I'm sure you can't be reading weird. So I said 500 and 10 and 2. And add to that, please, the anti-version of this. I want 3 anti-hundreds, 6 anti-10s, and 8 anti-1s. Right, that's the actual picture, what's going on, it's correct. There'll be some annihilations. Leaving 2 actual dots there. Or 1 annihilation. Leaving 5 anti-dots there. And 2 annihilations, leaving 6 anti-dots there. I was correct. The answer is 200, negative 50, negative 5t, negative 60. Absolutely valid. Totally fine mathematical answer. Math is very happy right now. Trouble is, society isn't happy right now. How could I fix this up for society?
reverse your explosion.
Oh, let's try it. Unexplode, de-explode, unexplode, reverse explode. So you take one of these guys and unexplode it. It came from what here? 10. So that's now 1 dot less, and an extra 10 dots there, is that right? Okay, so some annihilations go on. 5 annihilate with 5, leaving actually 5. The answer is 150 negative 60. Now what? Unexplode again! I don't know how to draw that sound of an explosion. 1 less there, an extra 10 there. If I did the annihilations, would that be 4? 144. Society might be happy with that. What's the traditional algorithm, by the way? Go right to left, of course, because that's how we always read in math, apparently. 2 to 86, you say can't do it. They should weep.
No, they just switch it and go 8 minus 2.
Yeah.
Ah, I don't blame them. They're employing my strategy. You don't like it, just avoid hard work. You're right. In fact, let me talk about that in a moment, but the traditional algorithm says you borrow 1 from here, go 1 less there, and change that 2 to a 12. Now, without understanding, that is bizarre. I mean, just change this number because you feel like it, and then turn this 2 suddenly all the way up to 12. But is it actually doing something correct in this model? I took one of these 10s and unexploded it, got 12. Now I've got 12 take away 8 is 4. 0 take away 6, can't do it. So you unexplode one of these guys, make it 10, not 0. For those that like the traditional algorithm, yesterday morning, I received a tweet from someone that said, they saw my stuff, said, well, why don't we just teach this? Why don't we have kids just go, 5 take away 3 is 2, 1 take away 6 is negative 5, and 2 take away 6 is negative 6. Because then they can see that as 200, negative 50, negative 6. So the answer must be, what's that? That's 150, take away 6, 144. Would that be a nicer version of the standard algorithm? If you don't want to get the whole dots and boxes stuff? Cool.
That is cool.
Understanding, just do it with understanding. In fact, I even make it better. If you really actually understand that ruler idea, 2005 take away 167. And I go, ugh. I go, ugh. But if you think of this as like 2 rulers, I want this one here. Is that what the difference is physically? What if I chopped off 5 from this end and 5 from that end? Does it still give you the same difference? So I might as well just make this 2000 take away 162. But I still don't like that. Let me chop off 1 more. Let's make this 1999 take away 161. Do you see how I'm just avoiding all sorts of carries now by making lots of 9s appear for me? I would love it if a kid just came up with that on his or her own. What powerful, flexible thinking to avoid hard work. Teach kids how to avoid hard work. Teach them how to work hard to avoid hard work. They're good at it when it comes to homework and stuff. Now do it in math class too. Avoid hard work. All right. Addition, multiplication, subtraction. Now comes the true part of the story. Grade 5 for me, back in Australia, unenlightened curriculum in the 1970s. We had to do long division. And back in Australia, in my day, this is how we were taught to do a problem like 276 divided by 12. We had to draw this crazy symbol. We had to write 276 and the numbers 12 within those symbols. Actually, this gave me a little bit of the heebie-jeebies. I never know which one was which. So you write like quotient or quotient or quotient or quotient, all these things are in one spot, and then quotient or quotient or quotient in the other spot. You might figure out from me that I have no fondness for jargon. Jargon is great when you need communication, but if you don't need it, it just gets more stuff to clutter the mind. Get rid of it. Just do it. Okay, so So this algorithm, I remember being such a good student, I was very good at pleasing my teacher. We were given worksheet after worksheet of these long division problems to do, and I could write them all out, I could get the right answers, I got my happy faces and my gold stars in my paper, and I remember being absolutely cognizant of not having a clue what I was doing. I never told my teacher, because my job was to be rewarded for getting it right. I was actually cognizant of not having any conceptual understanding whatsoever. In Australia, we're taught to do this. You say, okay, I know everything in math class so far has been right to left, but here go left to right. Switched all of a sudden. Everything was right to left with addition, subtraction, multiplication. Now it's only right to left to right. Bizarre. You go, how many times does 12 go into just 2? Which is weird, so the number's 276 is not 2. Plus it doesn't go into 2, you say, okay, don't be silly. But then it gets weirder. Okay, don't go 2, go the first 2 digits, 27. Why? The number's 276, not 27. Irrelevant. I was good, I did what I was told. How many times does 12 go into 27? Twice. So this part, we actually give me the real heebie-jeebies. Then I had to write the 2 at the top, and I was always nervous I'd get writing in the wrong spot. Apparently it goes there, it's where you write 2. Gave me the heebie-jeebies. So in Australia, you need to write 2 times 12 is 24, and then somebody do a little subtraction. And get 3. This is what you guys have to do? Something like this? Alright, if that isn't bizarre enough, it gets truly weird right now. In Australia, we need to draw an arrow, bring the 6 down, and find that 3 changes and becomes 36. Just changes. Just changes. And then we need to say, how many times does 12 go to 36? Twice. 12 times 3 is 36, because subtraction gets 0, apparently 0 is good, and the answer is 23. Whoa. Okay. Now, in my adult life, I know what's going on. It's dots and boxes. Here's a 10-1 machine. Here's 276. Here's 12. Now what does 12 look like? 1 dot next to 2 dots. Actually, let's be really clear on something. I didn't physically draw my 12 dots here. If I could, where would I have to draw the actual 12 dots?
In the one?
In the one spot. That's where the 12 dots really exist, but actually an explosion happened, so I've got an extra little dot over here. So if I were to physically draw the 12 dots, they're all right there at that level. Alright. Division. What is division? This is the help from the early grades. Be very clear. We're asking, I've got a whole bunch of 276 objects, and I'm asking how many 12s can I find amongst that collection. So we're looking for groups of 12. Here is my picture of 276 dots. They are all there. If I unexploded and unexploded, I've really got 276 dots in this picture, some explosions happened. Here's what 12 looks like. So I'm looking for 12s in this picture. That is, I'm looking for 1 dot next to 2 dots, anywhere in this picture. And I see gobs of them. For example, here's 1 dot next to 2 dots. Now that's not physically 12 dots. Where are the actual 12 dots if I were in that loop? Right here at this level. So there's one group of 12 at that 10s level. Any other 12s in this picture? Oh, yes. Another one at that 10s level. Yep, and then there's 12 dots. But if I actually do draw the 12 dots, they'll be right there, and right there, and right there. I've got 2 at the 10s level, 3 at the 1s level. The answer must be 23. I can see it. That's where they are. Now, let me help out young James 10. Let's imagine we could go back in time. What is this algorithm doing? Let's think about this in terms of dots and boxes. I first said, ask how many times the 12 will go into 2. In this picture, what's the 2? It says, okay, just look at those 2 dots. Do you see any 12 there? So what's the answer? No, don't see 12. Then I went from 2 to 27. So what am I actually doing in my mind's eye? I'm saying, okay, just look at this part of the picture, the first 2 boxes there. Do you see any 12s there? We saw 2, and that's why I wrote this 2 up here. Just like I wrote 2 up here, actually. What's all this subtraction business about? Yeah, so I've dealt with those. I can even erase them if I want to. And I've still got 3 dots left over to deal with. Now, the part that really threw me as a kid, this 3 measure becoming 36. What's actually going on? I'm just shifting my perspective. Now look at some more part of the picture. Now see 3 dots and 6 dots. Any 12s there? 3 of them. Got all the loops. Got no dots left over. 2 of the tests are all 3 of them. And actually, that algorithm makes perfect sense. Just that when it's taught to you as that's the algorithm, go ahead and do 50 problems every night for the next 6 weeks of your life. Joy, oh joy. Your turn. I want to know. I'll be nice to us first. By dots and boxes, what's 2783 divided by 23? My lip's a little weird here. Wants anyone? Alright, let me give you a problem. 31824 divided by 102.
No, because I can count. What does that look like? 1 space 2, so careful, there's a space there. Drawing loops might get messy, so you might figure out, might not be best to draw loops. But maybe I could just like do 1 space 2 like that. Oh, by the way, am I right? Do all 102 dots really actually belong right there? If I could undo all the explosions? Yeah. Any other 1 space 2s? Yep. And yep. And that. And 1 and 1, 2 and 2. Yep. So the answer is, good job. Okay, let me give you another problem. That space throws a lot of people.
Hold on.
Hold on. Oh no, you're on. Bring it on. 4061 divided by 31. Correct. I can just have a loop with nothing in it.
Nothing in it.
Yes.
Got it.
Yeah. Wow. I presented you with a problem. How do you figure it out? at least see one, at least do something. But now I'm feeling panicky.
Reverse explode.
First, unexplode one of them. Unkapow. That was 10. There's a 3, 1. And I think I chose yet again another really nice one. Beautiful. One more. And then I'll get us out of the early grades and bring us to high school. 2798 divided by 11. I'm going to give you another problem to contend with. So you might find yourself saying you're a little efficient, maybe just do a double whammy right there. Then you do a quintal whammy here. Am I right in doing it that way? You might get tired of drawing dashes, you might actually write the numbers maybe. There's 4 here, and it can match with 4 here, which is great. But now I'm nervous. What am I noticing? So the answer is 254. Depending on what grade level, you could say remainder 4. 4 dots yet to be divided. If you're more upper grade, you say 4 dots still yet to be divided by 11. Beautiful. Beautiful.
Or you keep going.
Or you keep going. What a novel idea. However, let's not keep going just yet, because let me actually bring us now to our area. So, there is absolutely nothing special about 10-1 machines. We could do all this work in a 2-1 machine. But they do this, computers do. You can do all this work in a 3-1 machine. You can do all this work in a 5-1 machine. You can do all this work in a 72-1 machine if you want to. Nothing special about 10-1. It's just our anatomy just has us humans fixated on the number 10. Math doesn't care which number you're in. So what I want to do is repeat all our work now in every machine possible, all at once. Now what do I mean by that? I'm going to do it in a machine, but I'm not going to tell you what machine we're in. It's just the mood I'm in. So this is a high school group. There seems to be a very favourite letter of the alphabet, but when you don't know something, what to call it. What's the favourite letter of the alphabet? X. Obsessed with X. But just to feed into that obsession, I'll call this an X1 machine. I'm just not telling you what I have in my mind for X. It could be a 10-1 machine, I'm just not telling you. It could be a 2-1 machine, I'm not going to tell you. There is 3-1, you just don't know. The mood I'm in, I'm not telling you. However, you do know dots here are always worth 1, and X of these explode to make a dot here, so it's going to be worth X. X of these is worth 1 of those, this is going to be worth X X's, which is what? X squared. X of these, X squared makes a X cubed, X to the 4th, and so on. So you know that much at least. And in fact, if I do reveal to you that actually X is 10 in my mind all along, is this really a 10-1 machine? 1, 10, 100, 1,000, yep. Or if I told you actually X is 2 in my mind, it's really binary, am I right? 1, 2, 4, there you go. I kid you not. I have kids go from this division, and I will tell them right now,
Please work out 2x squared plus 7x plus 6 divided by x plus 2. Go for it. Out of the blue. Let's just do high school algebra now. You can do it. I know you can do it. Do it the dots and boxes way. Just do it. Follow Nike. Just do it.
So 2x squared is 2a's. Times 7 plus 2.
So I can.
X plus 2. X plus 2 is
Mind blowing. Kapow. Hesitant actions will go like.
x plus 2. There's what I'm trying to get at is this. So I'm going to start here. Just throw it down.
Leave up. It's impossible.
Don't do that for my video. Take it back. Take it back.
One.
2x squared, 7x is in 1. It's 6, 1, sorry. And we're looking for x plus 2. What does x plus 2 look like? 1 dot and 2 dots. By the way, I know you're complaining at me for not having parentheses here, but you know what I mean. So do you see any 1 dot next to 2 dots in that picture? 1 there, 1 there, 1 there, 1 there, and 1 there. So what's the answer? Did this feel like deja vu? Is it absolutely identical? In fact, if I told you x really is 10 in my mind all along, what number is it really if x is 10? 276 divided by 12 apparently equals. The pictures are identical. I mean, I just drew my loop slightly differently. All this polynomial work, you can just say it's just grade 5 arithmetic all over again. It's just in base x rather than base 10. What do you do? Pictures are identical. Absolutely identical. Nothing new is going on. In fact, I'll prove it to you. Do this juicy beast, and you'll be fine. I bet you can do everything. Let's make it absurd. X to the 4 plus 2x cubed plus 4x squared plus 6x plus 3, all divided by x squared plus 3. I'll give you a little space problem on the bottom, but you can handle it. I know you can. If you can do that, we're golden.
Try to trick me.
Does this work with multiple variables?
Go for it. You can make it work.
Yeah.
You don't do multivariable polynomials in Alberta, do you?
He wants to do tonight.
Go for it, absolutely.
Okay.
Make it work.
Right, Dad?
I'll come with all like TV slogans. Just do it. Make it work.
Right?
Have
You'll
you
tell us
done
what
it
to guess.
before?
Sorry?
Have you done it?
I've played with it, yeah. Go for it. You make it work. Make it work. We don't have to stick with real numbers. You can actually do this in complex numbers as well. When you do double rows and stuff, real imaginary types. You can actually put this
One
And I'm taking
Yeah,
this squared divided by x squared plus 3.
Yeah, what's that x squared plus 3? What's x squared plus 3 look like? Yeah, it's one of those space
Yeah,
problems.
yeah, that's what you were doing. Yeah.
Yeah, 1 space 3, watch out.
That's what that was.
So keep your wits about you, this is the other part of all this. And of course make mistakes as you go along, that means you're figuring it out.
Where you can go 1 space 3. So. Oh, it's just
of case. Alright, so, I should point out what I'm starting to learn. It seems to be, from the feedback I get from talking to people, that polynomial division both is and isn't part of the Alberta curriculum right now. Everyone agrees that dividing by linear terms, or what do you call these things, monomials, I don't know, we don't know jargon, is definitely part of the curriculum.
Well,
And often people do synthetic division.
You have to be able to factor polynomials, don't you?
But then, you have to factor polynomials, and I believe there are questions like, here's a fourth degree polynomial, I'll give you one of the factors, tell me another one.
Or tell me what's left.
Or tell me what's left. In which case, that's really polynomial division.
Yes. That's the great
So it's not
Jason.
explicitly said, but it's there.
Tell me what.
It's not stated by.
So Jason, just arm me. Can you actually find the actual, I don't know what the word is, content standard that actually has, we must factor what are the DDADs? That'd be great.
Thank you, Jason.
It's right here. It's,
Awesome, Jason.
Sorry?
Thank you. Yeah, thank you.
It says, demonstrating understanding of factoring polynomials is degree greater than 2.
Do you agree? Better two, so we get into juicy stuff.
Limited to degree 5, so less than degree 2 to degree 5. And that's really all it says. Rational zeros theorem is beyond scope.
Say it slowly, what's that?
It's beyond scope, so they're not actually.
What's beyond scope?
The rational zero theorem.
Rational zero
They're
theorem.
not gonna-
Yes, rational
we
roots
have
theorem,
questions
okay, that's how I
on
know it.
But we do have questions where they'll have, say, a degree 5 polynomial. These factors will be what's left behind. And what's left behind might be a cubic or a square or a quadratic that you can't factor anymore.
Right, Jason, what's the actual standard number? What was the code for that piece?
It would be under functions and relations at outcome 11.
And what grade is that, Jason?
That's 30-1.
Okay.
NC has modeled the factoring of trinomial concretely or pictorially and recorded the process symbolically.
It's in there.
Sarah,
It's in there.
say it again.
That's 10C, so model the factoring of a trinomial concretely or pictorially
Right.
and record the process symbolically. That is algebra number 5.2.
Alge, was it 5?
5.2.
All right. Okay, now I've got some armor, thank you. All right, so the trouble is, this is wonderful and powerful, this is great. I think this would be spectacular for kids. What an epiphany for kids in grade, whatever this is, we're in high school. Where they suddenly see that place value work from way back in grade 2 is just the same story. Mathematics is repeating itself, just the context, the perspective you take on it gets broader and broader. It's not more complicated material, it's just more and more expansive view of what math is and can be. What a powerful message to kids. It's really the same ideas over again, and you are empowered to figure out yourself. The only trouble what I've done with you so far is I've been pulling the wool over your eyes. I've made this look too nice. I've been ridiculously nice, and I'm not convinced it actually works. Try this example.
Can you do that same question about put x squared plus 2 on the bottom?
Get to remainders and so forth? Was that what we're asking? Yes, you can.
Yeah, I actually copied down the question wrong and started very confused.
Do you get remainders happening?
Yes, I got a remainder in the, I got 1 in the x squared, 1 in the x, and 1 in the 1.
Okay, so there is you'll see a way to help with that.
That would be like a pretty short question.
Yep, we'll do that, hold on to that, don't, oh, it's that question with x plus 2 on the bottom, is that right?
Yeah, I
Okay.
wrote it down wrong.
We'll do it next, But however, see what the problem is. See that actually I've been troublingly too nice.
Thank you.
So one of these, 2
-3.
Everything I've been saying is a lie.
No x squared and 1 x
circles, didn't you?
Yes, add 2.
Yeah.
Yes. Hold on, times 2 plus 2 ones, 2 x's, 2 x's. Okay, are we good?
We have the right formula,
Yeah.
okay?
Yes.
So divide
X
by
plus
2.
Two.
So that looks like, that's really what that looks like.
Right?
Because the
Well, let's
numbers are
add
the
this
numbers.
side. Okay, yeah, so we'll go 10 here.
Yeah,
Oh, no,
that's-
can't Can't,
Oh, right,
can't,
right,
it's not
right,
because
right,
can't.
right, sorry, sorry, sorry.
That's what I tried to do last time.
Yeah.
So I'm not sure they're referring to it.
You know, add it. So let's add some here.
That must be
You're
63,
Then we have to.
Then we have to also add penalties. I'm gonna add 6 just because I want to. And then I'm gonna have to take away 6. This might not be helpful.
So it's actually like a degree 3 polynomial divided by bits.
Oh yeah, now it does work.
Yeah, that's so
So
what we
now
call
we
it
don't
appropriate. Think about it.
You added 6, we added 6 and gave 6.
Yeah.
Yeah, got it.
But I don't know if 6 was there.
Okay, so let's do it, so x plus 2?
Okay, so now what do we do? We don't have anything here.
Well,
I'm gonna
at
add
some
x
point, we want
to
kids to know that 24 is
Yeah,
breaking
still,
up
we need something here though.
and that's then the
It needs to do something, like you need to have something.
that's how-
So let's add 2 dots.
All right,
Let's add 2 antidotes.
this one is problematic.
Look, now I have this.
1 dot, no dots, 3 antidots, is that right? And x plus 2, what does that look like? 1 dot and 2 dots. Sorry? Oh, 2, I was thinking, sorry. All right, my reaction right now is an emotional one. I want to weep. All right, so yes, so we've got a problem. We've got a problem. Maybe actually everything I've been saying is supposed to be, I've constructed to be nice, we give a false image about how wonderful this is, but it's all actually a lie. So I'll give you something with meat to it. We do. Now, my job as a teacher could be seen as, I need to get kids how to do this, I will teach you how to do it right now. That's actually, in my opinion, not my job as a teacher. My job is to help you become confident, powerful, thinking adults, ready to try stuff, get it wrong a few thousand times, and persevere nonetheless, and think your way through it. So, I heard some people had a strategy what to do. I mean, I want to see 1 dot next to 2 dots, and I just don't see it anywhere. I don't even have a start. And then I heard someone say something about unexploded.
Yeah, but I got the wrong answer.
All right. So we've got 2 strategies right now. One is, all ideas are good ideas. There's nothing wrong with ideas. The real question is it a helpful idea? Does it lead somewhere or not in this particular context? Unexplode. If we unexplode, we can draw some dots here, unexplode, draw some dots here, and then we get some 1 next to 2 at least. Unexploding can be great. All right, so let's unexplode this dot. How many do I draw here? I don't know. There's an x1 machine. I'm not telling you what x is. If you knew I was thinking 10-1 machine, we'd know to draw 10 dots there. If I told you it was a 2-1 machine, you'd know to draw 2 dots there. I don't know how many dots to draw, I can't explode. I don't even know how many dots it's supposed to draw. Now some people might try to represent x dots in some sort of, symbolic way at this point. Go for it, maybe you can make it work. Could be a good idea. Seems hard to me, personally. That's just me. So now, I have a second emotional reaction, which is, I really wanted to weep. However, there is a life lesson here. If there's something in life you want, my advice is, make it happen. And deal with the consequences. Is there anything you'd love to see to go with this dot right now? Wouldn't it be lovely to see 2 dots here? So there's something in life you want? Make it happen. There it is. I've made it happen. But deal with the consequences. That's just changed the question. This box is meant to be empty. This fellow suggests keep it empty, like that. Is that box still technically empty?
Yes.
That's a good move. Now, it got me started, but I still don't know if it's helpful. So maybe we're going to reject this. Who knows? However, I think there's something else in life I want right now. Wouldn't it be nice to have something to go with those? Wouldn't it be lovely to have a dot here? Okay, if there's something in life you want, make it happen. And deal with the consequences. Alright, so at least gets me a second step. Still don't know if this is helpful. I'm doing something. So what did you just say?
I saw the lights go. I just saw the lights go.
Yes! I bet the epiphany back there was this. Look at this part. Isn't 1 antidot next to 2 antidots the exact opposite of what we're looking for? We have an anti-version we want right there at that level. In fact, we have another anti-version.
I figured that out.
So what's the answer? So actually we're refined. We're refined. Now, put some dots and anti-dots. Your x squared dot. You would like to see another dot next to it. So I bet you can keep whittling it down. You'll have some dots left over, so you'll probably have a remainder in it. Alright, so let's do another one. This time I really mean it. If you can do this one, we really can do them all. It'll be horrendous. I advise you to draw big pictures. Those loops are going to get messy. Alright, big space. Because this truly is the test. If you can do this, you are golden for life.
You golden, pony boy.
Stay gold.
That's what my true passion is.
Apparently, dividing, factoring fifth-degree polynomials is part of your curriculum. I've given you one factor. I'd like to know what the other factor is, please.
Did you skip any?
Did I skip any?
No, okay.
Probably.
I just need to know before I draw my boxes incorrectly.
Give yourself lots of space. It's going to get messy.
Okay. Only you had a big spot you could write on. That's.
So I know you erased it now, but did that get somewhere for you? On that x plus 2?
I ended up with, my last box still had 3. Also, another thing that I got was a positive pair and a negative pair, which I assume cancel each other out.
Yep.
No,
Yes,
you can do it like turtles.
And then I was left with 3.
So polynomial plus 3 gets
One of
divided by x
And
plus 2.
two of
So
these,
that's polynomial plus 3 over x plus 2.
seven.
Right.
Oh, it's -2, no, -2,
Yeah.
-2,
Yeah.
-2.
So you can totally fix it. Yeah.
And 7,
One,
-4,
and one for 6.
-1.
Is that what you know?
Yeah.
Okay. So what's this gonna look like? It's gonna look like. So is that what you got?
Yeah.
Okay.
Nasty.
Okay.
Have you ever heard of Daniel Tennant?
No, I have not.
Okay, he's a British guy, and he's a bit of a savant, but he still functions.
Oh, did you like Born on a Blue Monday?
Yeah, Born on a Blue
Yeah.
Day, that's it.
Yeah, the British book, yeah. Sorry, very fancy name.
Okay.
Yeah, so what's he doing now?
He does poetry and art stuff. He lives in France with his partner. But my question was going to be, did you hear about him just because of the way that he does his mathematics by imagining things as shapes, and then the way that the shapes fit together, give him the products. And
Exactly, and remember there's the pies on landscape, there's walking.
Yeah, right, right.
Stuff, yeah. Yeah. Yeah, very visual. I believe one of your competencies in Converter is like V for visual thinking.
Visualization.
Boy, are we doing that. We got a major checkpoint for that one. Very lovely with exploding dots. No Minister of Education or visualization can come down and say, you're not visualizing your kids.
Dot, anti-dot, dot.
Yeah, variable. Cool, it's all good. Oops. messy one.
Dot,
It is gross.
anti-dot. Dot. Okay, dot. Dot. Did you keep going after the decimal? It ended? I thought I almost had it. This one. I don't think I have anything left here. One, two, yeah. So we're wrong. How many should be here? 5?
I got 5.
Did you get 4 here? 4?
Yeah, 4, 2, 5.
Okay. So somewhere here I.
Because I ended up with a group of, like, from here,
From
there was a group of 5.
That's what I got too.
Five.
I got the 5.
And then it ended?
I got 4, 2, 5, but then I got messy and I couldn't see what I did with my
Yeah.
erasing. So now I'm stuck, but I'm pretty sure.
So then what happens? Was that
Right
end?
here.
It ended?
No, because then what I ended up with is I ended up doing an anti-version. I got an open, closed, open, and so this one ended up being a
A
negative.
negative 1.
Yeah.
But it was a negative 1 then.
So let's have a 10-minute break now where we finish this up and just have a break. And we'll come back after the break and we'll go through this one together as a group.
Yeah.
So if it's too frustrating, just don't worry about it because
So I got negative
it's
1.
messy.
Yes.
It's hard for kids and they have to like keep track of themselves. It's good lesson to kids, like being really precise with your doing and drawing.
Did you make it?
Well, almost.
Colours are very helpful.
Yeah.
Yeah. And I've got commentary on this, but this is pedagogy is what I'm doing right now.
So you, oh, so you got like an anti-dot